So I decided to make concentration start on its own section with a new video, so here we are with a new video. The concept of concentration, again, may be familiar to many of you. To many of you, it may not be familiar at all. So I'm going to try to start out by describing the idea behind concentration using an example with my cup of coffee again. So imagine that I have my cup of coffee. The volume of my coffee, let's just pretend it's 100 milliliters. I have 100 milliliters of coffee. It's unsweetened. However, I add a packet of Splenda to my coffee. Hopefully everyone will agree that my coffee will become sweeter. If I add 2 packets of coffee to my 2 packets of Splenda to my coffee, hopefully everyone will agree that the coffee will become even sweeter. And I can keep doing this, right? I could add 4 packets of Splenda to the coffee, and presumably, as long as it all dissolved, it would be even sweeter than when I had only added 2 packets of coffee. Now, we're not yet at concentration, but hopefully everyone will agree with that. 4 packets of Splenda dissolved in this coffee cup will be sweeter than 2 packets of Splenda dissolved in that coffee cup. Now let's pretend that I have a different coffee cup though. I have an espresso cup. It's much smaller. Maybe it only has 10 milliliters of coffee in it. And if I put 4 packets of Splenda and dissolved them in my 10 milliliters of espresso, and I took another 4 packets and dissolved them in this coffee cup, the question now is, which coffee is sweeter? Now let's assume that they're both made of the same type of coffee. Which coffee is sweeter? This one has 4 packets of Splenda, so does this one over here on the left. Hopefully you will agree that it's the one on the right that is sweeter. The reason that it's sweeter is because it has less amount of liquid, but it has the same amount of sweetener. It has the same amount of solute, or stuff that's dissolved, as is this cup, but it's dissolved in a much smaller volume, which means that there's much more of it inside of a certain amount of volume than there is over here. This is the idea behind concentration. Concentration is basically a way of describing how much solute, how much of something is dissolved in a certain amount of liquid. If the concentration of something is very high, that means that the amount of stuff that's dissolved is large for a certain amount of liquid. If the concentration number is very low, it means that the amount of stuff that's dissolved is not much for every certain amount of liquid. And more mathematically, concentration is usually written something like this. The concentration number equals the amount of solute, in this case it's the amount of sweetener, divided by the amount of solvent. In this case it's the amount of coffee that is doing the dissolving. So the idea is that this number, concentration, whatever that number is, can either be a big number or a little number or somewhere in between. And it will depend on the amount of stuff that's dissolved, and it'll depend on the amount of stuff that's doing the dissolving. To give you a more concrete example, I will talk about these in more detail. So if you wanted to informally describe the concentration of Splenda in my Dunkin' Donuts coffee, you could say that it's 4 Splendas divided into 100 milliliters. And that is basically equal to this equation down here. And 4 divided by 100 is 0.04. So what you could say is that the concentration of Splendas in my Dunkin' Donuts coffee is 0.04 Splendas for every 1 milliliter of coffee. That's a way of describing the concentration of Splenda in this container. You can do the same thing for the espresso cup too. But here it's 4 Splendas dissolved in 10 milliliters instead of 100 milliliters. Because it's 4 divided by 10, 4 divided by 10 is actually 0.4. So you would say that the concentration of Splenda in this espresso cup is 0.4 Splendas for every 1 milliliter of coffee over here. And if you look, 0.4 is larger than 0.04. What that means is the concentration of Splenda in this container is larger or higher than the concentration of Splenda in this container. And so that is basically the essence of what concentration is. It's how much stuff is dissolved divided by how much stuff is doing the dissolving. Now, again, I'm just re-showing you the formula here. This is a very general formula for concentration. How much stuff is dissolved divided by how much stuff is doing the dissolving. It turns out that there are many different ways of calculating concentration, and they all have this basic idea behind them. They all have this basic equation behind them, but there are actually many different equations, and they differ by each other in little ways. And so I'm going to show you, I think, 4 different ways of calculating concentration. And basically what that means is I'm going to show you 4 different equations. So they will follow on the next bunch of slides. So the first method that we are going to talk about that is a method for describing how concentrated something is when it's dissolved in a liquid is called the mass percent method. So that's written here. Sometimes it's called the percent by mass method, sometimes it's called the mass percent method, and sometimes people will refer to it as the percent M over M method, which is sort of shown here to the right. The formula for the mass percent method is this. If you want to describe the concentration of some material dissolved in some liquid using the mass percent method, then the formula is that you take the mass, or informally the weight of whatever was dissolved, that's the numerator, you divide it by the mass of everything, including the mass of the stuff that was dissolved, plus the mass of the liquid that was doing the dissolving, and that's the denominator. And then you multiply whatever that answer is by 100%. And that number that you get is called the mass percent method. So, excuse me, if this is a little bit confusing, if it seems like I'm putting the cart before the horse, let me give you an example. And this might help clarify what is going on with this equation. So the question is, what is the mass percent concentration of 8 grams of table salt mixed with 62 grams of water? So the idea visually is this. Imagine you have a beaker or a glass or something like that, and it has 62 grams of water in it, and you dissolve 8 grams of table salt into your liquid. So now we have salt water, basically. We have salty water. Now you could taste the water and you could say, well, it's salty. And then I could ask you, well, how salty is it? And you might say, well, it's really salty. However, hopefully you appreciate the fact that saying that something is really salty doesn't give you a very detailed appreciation for how salty it is. It would be nicer if we could sort of describe how salty the liquid is by putting a number on it, which is basically the equivalent of describing the concentration of the salt in your liquid. And one way of describing the concentration of the salt in your liquid is this method, the mass percent method. So instead of saying my salt water here is really salty, you can actually give it a number. You can say it's 5% salt using this method, or it's 10% salt using this method. So let's go back to this original question. What's the mass percent concentration of 8 grams of table salt mixed with 62 grams of water? Well, according to this equation, the solute is the table salt. That's the stuff that's dissolved. So the 8 grams of table salt will go in the numerator. It will also go in the left hand of the denominator here. So I'm showing that here, 8 grams of table salt in the numerator. It's also on the left side of the denominator here. However, we also have to include the weight of the water as well in the denominator. So basically, the mass percent number will be 8 grams divided by 8 grams plus 62 grams, all multiplied by 100%. I'm going to simplify this part over here. It will turn out to be 8 grams of table salt divided by 70 grams total, and I'm putting total there to emphasize the fact that we are talking about the mass or the weight of everything in this solution. Oops, let me go back there. So we're talking about the mass of everything in that solution. That includes the table salt that was dissolved in the liquid and the 62 grams of water. Altogether, the whole thing weighs 70 grams. So what you're doing is you're doing 8 divided by 70 times 100%. If you do that out, the number that you get is 11.4%. So if I told you that I had 62 grams of water and I dissolved 8 grams of table salt in it, you could tell me that the concentration of table salt in that water is 11.4% by mass. Or another way of thinking about it is that you would say the concentration of table salt in that solution is 11.4% using the mass over mass method. And if there were more salt dissolved, if there was more than 8 grams of table salt dissolved in 62 grams of water, you would probably say that the salt water tasted saltier. And in a similar way, if you dissolved more than 8 grams of table salt, this number would actually be bigger, which is another way of saying that the water would be saltier. The percentage would be higher. And so this percentage is sort of just a numerical way of describing how concentrated the table salt is in this particular liquid, in 62 grams of water. So that's the mass percent method. Just as another example, I'll ask you, what if you had 16 grams of table salt dissolved in 62 grams of water? And hopefully you see that 16 grams is more than 8 grams. So when you mix these two things together, it will be saltier water. The question is, will the percentage be higher than 11.4%? Well, it should be. And here you can see what's basically going on. You use the same formula to describe the concentration of table salt when you dissolve 16 grams of it with 62 grams of water. So we have 62 grams of water in our container. We throw in 16 grams of table salt. What's the concentration using this method? Well, now it's 16 in the numerator divided by 16 plus 62 in the denominator, all multiplied by 100%. And simplifying that becomes 16 in the numerator divided by 78 grams total. That's how much everything weighs together, the table salt and the water, multiplied by 100%. And the new percentage is 20.5% using the mass over mass method. Or usually people say the concentration of table salt is 20.5% by mass. So there you can see that this is saltier water and the concentration is higher than the percentage that we got on the previous slide. So that's the percent by mass method. There are a few other methods for describing for describing concentration. Each of the methods that I'm going to describe, each method has its good points and its bad points, or each method is good under certain circumstances. So this particular method, the percent by mass method, is good when you know the weight of both the thing that you are dissolving and the thing that is doing the dissolving. When you know the weight of both things, then this is the percent by mass method is the preferred method for describing concentration. There are times, however, when you might not necessarily know the weight or the mass of both of these things. And so there are other methods. The next method that we're going to, one thing that I should point out is I have a little recipe for how to compute mass percent, and it's pretty straightforward. You get the mass of your solute. That's the thing that's being dissolved. I'm going to call that A. Get the total mass of your solute and your solvent. So that's the mass of everything. And I'm going to call that B. And then you just do 100% times A divided by B. And the units are percent parentheses M/M. Now, the next method that I'm going to talk about is the next method for describing concentration is called volume percent. Sometimes it's called percent by volume, sometimes it's called percent V over V. This method or this formula should be very similar, should basically be almost identical to the percent by mass method that we talked about over the past few slides. So if you want to describe concentration using the volume percent method, volume percent is equal to the volume of the solute. In mass percent, it was the mass of the solute. Now it's how much space the solute takes up in 3 dimensions, divided by the volume of everything mixed together, the solute and the solvent, and then multiplied by 100%. So this is almost identical to the mass percent method, except instead of mass, we're using volumes, both in the numerator and in the denominator. So, question to work on. What is the volume percent concentration of ethanol? So ethanol is the alcohol that we drink when we drink alcohol. what is the volume percent concentration of ethanol when I mix 7 milliliters of ethanol with 43 milliliters of water? So, and basically we're going to use this formula up here. So just to give you a visual of what's taking place, imagine that we have a container with 43 milliliters of water, and then we are going to mix in 7 milliliters of ethanol. And the basic question is, what is the concentration of ethanol in the final mixture using the volume percent method? And so we have 7 milliliters of ethanol, 43 milliliters of water. The formula basically says that the solute, the thing that's being dissolved or the thing that's being mixed in, the amount of that material is put in the numerator in volume units, so we're going to use 7 milliliters. And then the denominator is both volumes added together. So the total volume of the whole mixture is 7 milliliters plus 43 milliliters. That's on the bottom. And then this top number divided by the whole bottom number is multiplied by 100%. I'm simplifying the denominator here, so it's 7 milliliters of ethanol divided by 50 milliliters of the entire mixture. That's why I put total here. And then you multiply that by 100%. 7 over 50 times 100% turns out to be 14%. So what you would say if you mixed 7 milliliters of ethanol with 43 milliliters of water is you would say the concentration of ethanol is 14% by volume, or 14% using the volume over volume method. And so this is very similar to the percent by mass method that we discussed on the previous slides. The only thing that's different is that we are using volumes of these materials instead of masses of these materials. So this method is typically used when the things that you are mixing together are both liquids. So you don't need to know how much they weigh, you just need to know how much space they take up in this case. So you'll very often use this type of calculation when both of your materials, the solute over here and the solvent over here, are both liquids. And as an example of that, a lot of times you will hear on commercials and elsewhere, you'll hear discussion of alcohols, so beer or wine, things like that, and they will describe the concentration of alcohol in the beer or the wine by saying that it's, well, in this case they say it's 14.5% by volume. What they're telling you here is they're using the volume percent method that we just discussed on the previous slide to describe how concentrated the alcohol is in this particular wine. So what they're saying is that for every 100 milliliters of wine, 14.5 milliliters turn out to be alcohol. And so that's just a common thing that you might have heard before, and now you probably have a better appreciation of what they actually mean by that. They just mean that they're measuring concentration of alcohol using the volume percent method. So that's the volume percent method. There's a third method that is often used. I forgot again that I am going to give you a little recipe for volume percent. So here it is. Get the volume of your solute, call that A. That's the liquid that you're mixing in. Get the total volume of the solute and the solvent, call that B, and then the volume percent is equal to 100% times A divided by B, and the units are percent parentheses V/V, which means volume over volume. So that's it for volume percent. The next method sort of combines the first two methods that we've discussed. It's called mass percent volume, or mass over volume percent, sometimes abbreviated percent M over V. The mass over volume percentage, the formula for that is that you take the mass or the weight of the stuff that you're dissolving, the mass or the weight of your solute, and you divide it by the volume of the entire mixture after the stuff has been dissolved. That's why I have solution here in bold, because solution basically means the solute and the solvent mixed together. So you take the mass of the solute divided by the volume of the entire mixture after everything's been dissolved, you multiply by 100%. So hopefully you can see that it kind of combines the first two formulas a little bit. In this case, you tend to use this shows up in biology a lot. You tend to use this formula when you know the mass or the weight of the stuff that you're dissolving, and you can measure the volume of the final material pretty easily. So sometimes this is used in biology. Here's an example. What's the mass over volume % concentration of table salt in a 100 milliliter solution that has 10 grams of table salt dissolved in it? So basically, I'll show you a cartoon version of what's going on. You have 100 milliliters of salt water because there's salt dissolved in it. It turns out that there are 10 grams of salt dissolved in it. And so what I'm asking is, what's the mass over volume % concentration of this solution over here? And so to do this, we're just going to use this formula up here. And it's pretty straightforward. We know how much the weight of the table salt that was dissolved, that goes in the numerator. We know the volume of the entire mixture is 100 milliliters. And then we multiply that. We do 10 grams over 100 milliliters times 100%. And so if you do that out, it turns out to be 10% by mass over volume. So what you would say if you wanted to describe the concentration of table salt in this mixture, you would say that that mixture is 10% using the mass over volume method, or 10% parentheses m over v. And so this is just a third way of describing the concentration of something that's dissolved in a larger liquid. So again, each method that I've described so far has its good points and bad points, and situations where it's more useful to use one method over the other. This method is preferred to be used when you know the mass of the stuff that you're dissolving, and it's easy to measure the volume of the stuff that you end up with. And here's the recipe for doing that. You get the mass of your solute, call that A, preferably in grams. That's typically how it's done. You get the total volume of your solute and solvent, which basically means the volume of your solution, and call that B. The unit should be milliliters, so grams on top, milliliters on the bottom, and the concentration is 100% times A divided by B, and the units are percent parentheses m/v. So those are three sort of relatively commonly used methods for describing concentration. There is a fourth, which is probably the most difficult, and so here it comes. It tends to be used in chemistry a lot, sometimes in biology labs as well. It's called molarity. This is a fourth method for describing concentration. So by the name molarity, you can probably guess that this method for describing concentration deals with moles. So just as a refresher, 1 mole is 6.02 times 10 to the 23 things. Usually atoms or molecules is what you're talking about. And how many moles of something, again, just as a refresher, is how many groups of 6.02 times 10 to the 23 things that you have. So if you have 2 moles, you have 2 groups of 6.02 times 10 to the 23. Molar mass is how much one group of 6.02 times 10 to the 23 things weighs. And the way that you can figure this out for molecules is you look up each individual molar mass in the periodic table and add them together for your molecule. So the molar mass of sodium chloride of table salt turns out to be about 58.4 grams. So if you have this many table salt molecules, that entire pile will weigh about 58.4 grams, and that's going to become important when we talk about this method. And so just to summarize, 1 mole of table salt weighs about 58.43 grams. So the concentration method that's used when you use the molarity method, the formula is shown here. Molarity, it's sometimes called molar concentration, is equal to the number of moles of solute. So the stuff that you're dissolving, you convert it to moles. You figure out how many moles of it you have, and you divide it by the number of liters of the entire mixture after everything has been dissolved. And so these units you have to pay attention to very closely in this case. You need moles on top, moles of what you dissolved, and you need liters on the bottom. And in many cases, with these types of problems, you won't be given liters. You might be given milliliters or microliters or something like that, and you'll have to convert them to liters. And in a similar way, you might not necessarily be given moles of the solute. You might be given grams of the solute, and you'll have to figure out moles. So those types of issues, and the fact that sometimes people are sort of confused by moles, makes this method maybe a little bit more difficult than the first three that we discussed. However, we're going to do some problems just to try to familiarize yourself with them. We'll do a few problems, and this one is relatively straightforward. What is the concentration, and really what I'm asking here is, what is the molar concentration, using this method, of 1 mole of table salt dissolved in 2 liters of water? So just to give you a visual, pretend this container now contains 2 liters of salt water. It's salt water because we have dissolved 1 mole of table salt into those 2 liters. And then I am asking, what is the concentration? And so basically we need to use this formula up here. Do we know the number of moles of solute? Yes, we do. It's 1 mole of table salt. Do we know the number of liters of the entire mixture? Yes, we do as well. It's 2 liters. So in the end, this is a pretty simple problem. It's 1 mole of table salt divided by 2 liters of water. 1 divided by 2 turns out to be 0.5 moles of table salt for every 1 liter. And you could write the concentration this way. You could say that the concentration of table salt in my 2 liters is 0.5 moles per liter. And that's what the per liter is down here. However, the concentration using molarity has its own special unit abbreviation. It's the capital M. So more often than not, if you are describing the molar concentration of something dissolved in some liquid, you will describe it in moles per liter, but you won't keep those units. You'll just abbreviate moles per liter as capital M. And so what you would say, the way that this is spoken by chemists and biologists, it's not actually spoken 0.5 molarity, although many beginning students want to describe it that way. It's actually pronounced 0.5 molar. So if you see the capital M, that is the abbreviation for molar concentration, and what the capital M means is number of moles divided by number of liters. So that's sort of the first problem with molarity. That was pretty straightforward because I gave you the moles and I gave you the liters. Here's a slightly different one. What's the molar concentration of 16 grams of table salt dissolved in 3 liters of water? So again, just to give you a visual, let's look over here. We have a mixture that contains 3 liters of salt water. It's salt water because we have dissolved 16 grams of table salt into the water. The question is, what's the molar concentration? And so for molar concentration, you need number of moles of stuff that was dissolved, number of liters of the solution. We actually know the bottom number. We know the denominator because it's shown here. 3 liters is the denominator. We don't know the number of moles yet because I gave you the information in grams. So this is going to require one additional step. And if you remember from the previous units, I told you that if you know the formula of something and you know how many grams of it you have, you can figure out how many moles of it you have. So even though this isn't moles and we can't plug this number into the numerator, we can actually convert this number into moles. And then we can use whatever answer we get, we can use that in the numerator to figure out our answer. So, if you remember a couple of slides back, here I'm basically just rewriting this equation using the information that we know. Molar concentration is equal to, I don't know how many moles of sodium chloride yet, divided by 3 liters of the entire mixture. So the question is, how many moles of sodium chloride is 16 grams? And if you remember from the couple of slides back, we said that 1 mole of sodium chloride, so let's focus on this fraction over here, 1 mole of sodium chloride is equal to 58.4 grams of sodium chloride. But we don't have 58.4 grams, so we don't have 1 mole. We have less than that. We have 16 grams of sodium chloride, so I'm saying how many moles of sodium chloride is 16 grams, and I'm calling that Z. And if you cross multiply and divide, Z turns out to be 1 times 16 divided by 58.4. And if you do that out, it turns out to be 0.27 moles of sodium chloride. So another way of describing 16 grams of table salt is to say that you have 0.27 moles of table salt. So this is how many moles of table salt are dissolved in our 3 liters of liquid. And this is the number that we have to put into the numerator up here. So in the end, the molar concentration is going to be, in this case, in this problem, the molar concentration of salt is going to be 0.27 moles of salt divided by 3 liters of the entire mixture. And if you do this out, 0.27 divided by 3 will equal 0.09. And so if you wanted to describe the concentration of 16 grams of table salt dissolved in 3 liters of water, you would say that it's 0.09 molar. And that's just another way of describing the concentration of something dissolved in a solution. So there's sort of a little recipe again for how to compute molar concentration or how to compute molarity. Basically, you have to get the number of moles of your solute, call that A, get the volume of your solvent in liters, call that B, and then it's A divided by B, and the units are basically pronounced molar, and the abbreviation is capital M. And again, just to emphasize, I won't do one of these types of problems, but very often you will see a problem where the information, the volume is not given in liters. It'll be given in milliliters or gallons or something like that, and you'll have to convert it to liters. So again, if I gave you a problem like that on an exam or a quiz, I would give you the conversion information, but you would have to realize that you have to convert whatever unit of volume you have back into liters to do these types of calculations. So that's it for molarity. There are more complicated problems that I will describe in the next section.